Yeah, Sahib's going to present on his internship this summer at CCL, and I just want to say before going that Sahib's a high school student, and I'm really been impressed with everything he's been able to pick up this summer. So and everything that he's kind of looking forward to doing afterwards, because this is not the end for Sahib. He's going to keep working with CCL through the fall, just in a different capacity as school starts. So Sahib, take it away.
So before we get started, we might also, does everybody know what the BioArtBot is? Raise of hands. Okay, so
Kind of.
kind of, I should probably explain. So the BioArtBot is an autonomous pipetting mechanism. Oh, it actually looks like everybody knows, but I will do it anyway because, for the sake of for the people. Anyway, BioArtBot is an autonomous pipetting mechanism that uses a XYZ trained to basically pipette different amounts, volumes of liquid bacteria medium onto plates to form patterns and basically in an endless variety of ways. But it can do so at a very accurate level, and which you don't really get if you do it by hand. So that's why it's an ideal mechanism. So let me just share my screen, and I will start with my presentation. So that's just a quick recap of what BioArtBot is, and why it's important later on in the presentation. Anyway, so I'm gonna share. There we go. Can everybody see?
Yep.
Yep.
Cool. Okay, so I'm sorry, my presentation about my experience as an intern at CCL this summer. So everything I did at CCL can be sorted into lab training, 2 experiments, and I'm planning my internship going forward outside of summer. We can start with the basic lab training I did at CCL. So the incubating shaker, chromatography machine, autoclave, and transilluminator are a few, but not all of the things, all of the labware I learned how to use at CCL. I also learned how to plate agar and LB broth, grow bacteria on plates, and how to make growth media for the BioArtBot, as well as programming and manipulating the code of the BioArtBot itself to perform a wide variety of functions. Once I had done my basic lab training, Mr. Dobbs said about creating different ways for me to apply my training through the use of experiments. In experiment 1, he told me to try and find the effective viscosity of the growth medium on E. coli growth in the BioArtBot. So the growth media in reference to the BioArtBot is the essentially the ink that we use. So if you think of the plate as a canvas and the bacteria, which we are putting onto a plate as the growth media, it is basically the ink. And what happens is we have bacteria which express different proteins and pigments, and we get basically different colored ink. And we put that onto our canvas or plate in different ways. And once they go into the incubator, they are able to express the pigment and create like works of art, basically. So the hypothesis that I came up with was if the viscosity of a growth medium is increased, then the width of the colony will also increase. And the idea behind this experiment was to get more pronounced colonies of bacteria, because we were seeing that with specific types of growth media, we would get different results. We would get colonies that would get pixels on, like, if you think about it that way, that wouldn't really touch each other. So you could see the agar in between them, and sometimes you would get overlap between growth colonies, between bacteria colonies, and that wasn't ideal. So to get more pronounced colonies of bacteria, we went about researching if viscosity had an impact on what we were doing. So the types of media or ink we used in the experiment were LB broth, which we used as a control, which is basically the bacteria on its own. Basically, the ink has nothing in it except the bacteria, LB broth, and that's basically what we use for an ink. We used 90-10 mix of LB broth and agar, a 95-5 mix of LB broth and agar, sodium alginate and LB broth because there's research about how sodium alginate may affect bioprinting, and we'll get into that later. But we wanted to see how it would work, and we had some sodium alginate, so we wanted to see how E. coli would react to it. And we also used 25% glycerol and 50% glycerol because I know right now in the lab when culturing bacteria in a liquid media, we use 25% glycerol. So as you can also think about this as a control almost. Anyway, this is the procedure that we used. It's very simple, straightforward procedure. I won't go over all of it because it's way too much writing. And I was told to keep this to a 10-minute maximum. So if anybody wants to see the procedure, we can go over it at the end following questions. So basically what we did was we designed a template to grow the bacteria as a dependent factor in everything, in all the plates that we designed using different inks. And everybody can see my mouse, right? So we used these 18 points, and we used two different types of bacteria. We used bacteria with the teal pigment, and we used bacteria with the blue pigment in order to test the growth of the colonies, because obviously different proteins require different levels of energy for the bacteria to produce, and maybe that might make a difference. So we decided to go with blue and teal, and we spread the colonies far apart from each other when we were testing the points. So these specific 18 points for blue and 18 points for teal. So we would get an accurate measure of the colony diameter and therefore area. This was our best plate, and by far the plate which had the widest colonies. This is the 50% glycerol plate, and as you can see between the purple and teal, purple and beige bacteria, they have the, when using 50% glycerol as a growth media or ink, it had the widest, which you'll see later on. But I would like to point out that we started using blue and teal, and the bacteria produced purple and beige. So that was interesting. Anyway, we decided to now start calling it purple and beige, but this is basically the colony diameter data. And as you can see, 50% glycerol has the highest diameter, with a diameter of 3.86 millimeters, whereas sodium alginate, 25% glycerol, 90-10 agar, 95-5 agar, and the control had significantly less diameters when in regards to the colonies. And 50% glycerol was also the growth media with the highest viscosity, second to sodium alginate, which was also quite viscous. So as you can see, sodium alginate, the second most viscous media, had a diameter of 3.76. 50% glycerol, which was the most viscous, had 3.86, and everything pales in comparison. Everything else pales in comparison. Now going by the area of the colonies themselves, in order to visualize the trends, we decided to make a box plot, box plots to represent all the data. So basically, essentially, with a box plot, what you want to do is you want to look for rectangles or boxes which have the smallest overall size, because that basically tells you that they had the most constant trend. And essentially, if we look at 50% glycerol beige, which is B, so P is purple, B is beige, we can see that the size of the rectangle and the size of the outliers, which are basically the lines going from extruding themselves from the rectangles, are the smallest. So 50% glycerol and the controls were had the most ideal growth media, were the most ideal growth media according to our hypothesis, our conclusion. So basically in our conclusion, we said a great candidate for future work with the BioArtBot would be 50% glycerol, which was the most viscous of the media and produced colonies with the highest diameter, area, and consistency. So that was experiment 1. Experiment 2 is still in the works right now.
So before we get on to experiment 2, it occurred to me that I think E. coli can consume glycerol. Is that correct? Can grow on glycerol?
Yeah.
So you're essentially giving it a richer growth medium, so you're going to get bigger colonies because you have more growth.
Mm-hmm. Yeah. Essentially, yeah, that's basically, yeah, pretty much, yeah. Because basically, even the agar had LB, but I guess we're kind of giving it, we're putting the E. coli on steroids by putting in the glycerol.
Mm-hmm. Yeah.
That makes sense. Yeah.
So if you just want to isolate the effect of the viscosity, then the experiments with alginate and with agar would be more relevant, I think.
That's probably true. Oh yeah. When we actually the agar might not be that ideal because when we use the agar, the BioArtBot couldn't handle the agar for some reason, and it created some colonies with really small diameters and some colonies which were quite huge. So there was you couldn't even see it. So there was a wide variety when it came to agar, as you can see through the box plots.
So when you say it's 5% agar,
yeah,
you don't mean actually 5% dry agar, right? Because that would be very, very solid.
Yeah, I'll field that because I made these solutions. It's a rough approximation of saying that you taking the mixes of both of them and sort of normalizing each mix such that you had to add the gosh, how do I want to say this? So that you kind of add them up to the amount for one that's required for 1 liter. And
so the 5% would be essentially off an agar gel, right? Which is typically 1 or 2%.
Oh yes, yeah. So it's taking the LB agar mix and the LB broth mix, and then I just said, okay, imagine we're making 1 liter. I'm gonna make add enough powder for whatever 5% of a liter is, 50, I guess, 50 mils, and then 950 mils of the broth amount, and then the same for 10. And in fact, the 10, that box you can see at the bottom, was it in fact did solubilize or solidify in some ways, and it clogged the pipette.
Yeah.
So I have a question about exactly what you're talking about. So how did you determine those proportions, 95 to 5 and 90 to 10, as opposed to, like, I don't know, 75 to 25 or whatever? How did you narrow it down to those?
I was a total range finding experiment. I just picked some numbers. And in fact, Sahib, I think you saw this. I started with assuming 90-10 and 75-25, and 25% agar. It's just solid. It's just like not very solid agar is what you end up with.
Yeah, I remember that. Yeah. It would. I remember the results from that. Yeah, it was solid.
Or what about going the other way, like 97.3, so you even have smaller proportions of agar to, or let's say 99.1 or something like that. What do you think that would do? It seems like going in that direction, you might get a better result, right?
Yeah,
well, right now they're already indistinguishable from the control, so.
That's true, yeah. And the control did actually turn out quite well. It had the most consistent between the beige and the purple themselves. But you might notice the disparity between the beige and the purple. That might just be because one of them is because they're producing different pigments. But yeah, the controls themselves actually had the least amount of outlier and was quite consistent when it came to diameter. As you can see, the control also works.
So if we want to revisit this in the future, there's a couple of other hydrogels we could use to increase the viscosity. Xanthan would be an obvious one to try. There's a couple of other ways of modifying the viscosity.
So like xanthan gum, or okay. So yeah, we should definitely do another round of this experiment. We should probably isolate the ones that we know that work. So probably sodium alginate, glycerol, maybe obviously control, and then maybe add some new growth media, including xanthan gum. That would be, yeah, we should probably, we'll do that actually. Yeah. Anyway, so that was experiment number one. And this was our conclusion that basically, new conclusion is because tryptophan glycerol basically just gives it a boost in metabolism, sodium alginate or control might be better.
Mm-hmm.
So experiment number 2 is not completed yet. We are still working on it because experiment number 2 is in regard to the volume. So when the BioArtBot prints, it prints 1 pixel at a time. So if I go back to the template that we used, imagine each pixel on this canvas is basically the square. And what happens is each of these squares is a possible point for the BioArtBot to put down a specific volume of liquid media with bacteria in it. So by changing the volume that we dispense at each point, we basically come up with different results. And what we wanted to figure out was, because we were experimenting with 0.1 and 0.5 on the BioArtBot, we wanted to figure out what was the ideal dispensing volume for each pixel. And we wanted to do it all at once. We could easily just print them out one at a time, but we wanted to print out all 5 of the canvases at the same time, and each of them would have a different volume while using the same template. And we had to manipulate a lot of code for that. So that basically meant changing every single aspect of the code, from how much ink we would use, the dispensing volume, the pixel for loop, which would basically how you would basically print the pixels, because usually the BioArtBot does it by color. So regardless of the canvas, it would go by color. So all the blue pixels first, then all the teal pixels. But we would have to change that in order to make it work by the volume. So all the 0.1 vol pixels, then all the 0.2, 0.3, 0.4, 0.5. So anyway, that we're still working on it. So we should expect to have the results before August 31st, ideally. So I'll get back to you on that.
When we're looking at different volumes, especially very small volumes, we may also want to consider that the tips we're using are fairly fat in terms of putting a dent into the agar. So we can get these lure lock needles. You can get them very fine. That would only make a very small stab into the agar, essentially. That might be interesting to experiment with.
Oh, what UL are they?
Sorry?
Oh, the tips. What volume are they?
So you can get lure lock needles of any kind of width you want, essentially.
Oh, okay. Cool.
Yeah, so you can do small fractions of a millimeter. Because you have a certain pixel size limitation in terms of how fat the actual pipette tip is, right?
Yeah. That's true, yeah. So, yeah. So what were they called again? I'm just writing this down as we go.
So there's a general sort of locking systems called Lure Lock, LUER. And it's a way of attaching, fluidic lines and stuff like that. But there's a set of needle tips that you can buy of different sizes that have the lure lock connection. We may need to 3D print a connector between the pipetters and a lure lock, but I think that could be arranged.
That's perfect. I'm glad that we didn't run the experiment yet, because we were actually having some trouble pipetting the right amount. There was a level of uncertainty there, because we would tell the BioArtBot to pipette a specific volume, and we would have no idea whether it would pipette that exact volume, because it looked like it was running out of volume within the pipette itself really quickly, and it looked like there was way more than there should be.
And printing 0.1 microliter, that's going to be hard for a robot as well.
Yeah. So lure lock needle tips. Cool. Anyway, so that brings us to the final phase of our final section of the presentation, which is basically my future internship plans. Essentially, what I wanted to do ever since I came into CCL was to bring bioprinting and a bioprinter into the lab, or probably make it ourselves, ideally make it ourselves. And I started researching methods we could do this. So as a next step of my internship, that's basically what I want to do. And my research took me through 3 different types of bioprinting. So the most common of which is using scaffolding. So essentially, when you're bioprinting, you're using biomaterials that are very fluid and they really have no structure at all. Scaffolding acts as basically what it is, scaffolding. Anyway, it's a material with high porosity and has basically lots of pores in it, as you can see from the top right image, that ensures cellular penetration and basically the diffusion of nutrients between the cells that are clinging to the scaffolding itself. So through the use of scaffolding in the top right images, bottom right images, and bottom left images, we can bioprint different cells. But I also learned that scaffolding is very hard to use and requires an immense amount of skill and time. So something that I don't have. So I went about researching other methods we could bioprint without the use of scaffolding, which seems to be the most common method. And I came up with 2 results. One of which is in a paper from UC Berkeley called parallel multi-layer cryolithography. And essentially, parallel multiple layer cryolithography is 2D printing, 2D bioprinting, in which you have one mechanism which prints a 2D layer of cells and then places it in cryogenic fluid, basically essentially putting the cells in stasis. And this is much faster and easier than printing with scaffolding, because when you're printing with scaffolding, you're basically doing it linearly. You're doing everything in one go and then you're done. But that usually promotes a bit of cell decay. And in order to avoid it, the parallel multi-layer cryolithography device does it in steps. Basically, you have one 2D layer and you put the cells into stasis. And because cells are hydrophilic, you place the cells, the 2D layer of cells, onto a hydrophilic surface, and then you can transport them anywhere. And in the image to the top left, which is the big image, this is the setup from UC Berkeley of the parallel multi-layer cryolithography device. As you can see, there's a robot arm involved, and you have these 2 mechanisms on either side of the laptop. The first mechanism basically prints the 2D layer and then lowers it into a tub of cryogenic fluid. And then the robotic arm takes that plate and then flips it onto another more hydrophilic surface so that the cells can be easily assembled. And once you have enough 2D layers of cells, you can essentially have a 3D structure that basically can be taken out of stasis over time and can be put into stasis whenever you want. So basically, it's more effective than printing everything in one go onto a scaffolding, which promotes cellular decay. The third method I found out, the other method I found, which avoids the use of scaffolding, is the use of hydrogels. So scaffolding, the scaffolding itself is made with unique materials that promote interactions between the cells. And a diffusion alone between the cell and its environment isn't enough to keep the cell alive. So in a paper by Thomas J. Hinton, he basically says, he talks about how cells suspended in hydrogels can interact with one another, and how it promotes cellular, basically, interactions between the cells, and therefore, without the use of a scaffolding, does not allow the cells to decay, and also allows for the diffusion of nutrients. This is a snapshot of the paper from UC Berkeley, parallel multiple layer cryolithography, which is $25 off the journal, which was very angry because every single paper I went to was either $25 or $50. So I ended up emailing the authors of the paper in order to get them. I didn't know about this when I joined CCL, but apparently there is a huge disparity between publishers and the people who write the papers. Publishers overcharge for the paper, whereas the people who write them and the scientists just want that information out there. So, I mean, how can people access the information if you're charging huge amounts of money for them? It doesn't make sense. The publishers are just trying to make a profit off of this, and the scientists just want that information out there. Sorry, I had to bring this up. I'm sorry. Okay. Anyway.
Has Tim told you about the glory of Sci-Hub?
Yes, he has, but I haven't gotten around to using it yet.
Yeah.
Anyway, thank you for listening. Any questions?
Nice work, Sahib.
Thank you.
Anyway, great presentation, very articulate, well thought out, great slides. That was
Thank you.
good.
Yeah, I use
That was
wonderful
wonderful.
AI.
Wonderful, Sahib. Thank you for sharing.
Thank you, Eddie.